Okay, for our second video on the Mann-Whitney test, or also known as the Wilcoxon-Rank sum test, we're going to focus on another example and also how it works. So this is kind of part two regarding the Mann-Whitney test and these non-parametric equivalent tests for T-tests. So if you didn't watch the first video on Mann-Whitney test, go back and watch that and then come back and watch this one. So moving forward, in the last video, I created kind of a fake data set for 9 families living in, we'll call it Town A, and the poorest person or poorest family made $19,000, and then there was a millionaire family that made $1.2 million. Now I've created another fake town income set, and we've got $45,000 all the way up to $60,000 for the highest income. So we've kind of got these 9 communities in Town B. Now you may be interested in creating a comparison here between Town A and Town B. You may need to ask yourself whether or not Town A has significantly higher income than Town B. That might be something that you have to figure out. It may not be Town A or Town B. It may be sample A and sample B from whatever research you're doing. So you've got to then compare these incomes, and you may have a tendency, without having this class or maybe an elementary basic stat class, you may think, well, I should probably just use the T-test because that's what you know. But the Mann-Whitney test is what's appropriate when we have skewed data. So if we look at Town A, we can see Town A has a median income of $30,000. That's a measure of central tendency for that town. The other measure for central tendency is heavily skewed. It's 158,000. No, 8 of the people in that, 8 of the families in that county or that sample make less than that. There's only one that makes 158,000 or more. It was the 1.2 millionaire. It was this one, 1.2 million. So is that representative or not? Now, in the case of Town B, it's a little more balanced. We have the median being 43,000 versus the mean of 43,666. So you might have a tendency, without doing a normality test, just to think, well, we'll just do a T-test, which you can do. So you do the T-test by either pointing and clicking in Stata or using a software of your choice or manually entering the command. So we're going to do a T-test comparing the income by town, Town A versus Town B, and we'll assume unequal variance. And we see that the average, the same averages that we had from our sum command earlier, the same averages we see. Group A, $158,666. Does this mean? Group B, $43,666. So this one's way higher than B. And we go down and look at the p-value for whether or not they're statistically different or not. And the p-value is 0.4030, 0.4030, which is higher than 0.05. So that's higher than 0.05. So there's no statistically significant difference between Group A and Group B. So despite the fact that this is a lot higher, the T-test did catch it and shows that there's no statistically significant difference between these two based on that average, even though that average for Group A looks so much higher. The reason why it fails, a big reason, is look how huge these standard errors and standard deviations are in this confidence interval around the average. So the T-test says no statistically significant difference between the two. Now, you should ask yourself before you even bother with the T-test, which test is appropriate, the T-test or maybe the Mann-Whitney rank sum test or the Wilcoxon-Rank sum test, also known as the Mann-Whitney test. Which is more appropriate? Well, we see for Town A, the one with the $1.2 million family, that the p-value for the normality test is 0.00000 or less than 0.0001. When we see low p-values, we should be telling ourselves, aha, something is statistically different. So in the case of the normality test, this one, town A, is statistically different from something. What is it statistically significantly different from? It's significantly different from normal. So since town A is not normally distributed, according to the Shapiro-Wilk test, we should probably use a non-parametric test. And town B, remember the one with the average and the median that were about the same? Well, guess what? It's normally distributed, so it suggests we should use a t-test. Now, what should you do? Well, whenever you have one of the distributions you're comparing being not normal or not parametric, you should use the non-parametric test. They say it's more conservative, is what I've heard. Political scientists apparently now are much more apt to use non-parametric testing about all the time because it's what they tend to use because they often are using or assuming that they're using non-parametric data. But in our case, this one's non-parametric, that's parametric. We will use non-parametric, so we should probably use the Mann-Whitney test. So we do the pointing and clicking like we did on the last video where you go to statistics, non-parametric statistics, and then you click down on the Wilcoxon-Rank sum test. And then once you get there, we're going to be comparing, in this case, at a variable called income and a variable called town. So we're interested in whether or not these two, income by town, if there's a difference between town A and town B, just like the t-test. So I click on OK. It runs it. It actually runs this command, rank sum income by town. We see town A had 9 observations. Town B had 9 observations. And then it gives us these things called rank sums and these expected values, which may not make any sense to you right now on what the heck this is all about. It's not the mean, it's not the median. What the heck is that? So we'll come back to all of this in a second. But what you'll see in Stata, it'll be in black text just like the rest of Stata's text. You'll have the probability of greater than 0, whatever. This is our p-value down here. And it's actually using the Mann-Whitney U distribution. And the p-value is 0.0517. So it's almost significant. So it's saying that the rank sum that we observed here for town A of 63.5 is almost different than the rank sum of 107.5. It's saying that town B is not statistically different from town A. It's 0.05, but boy, it's awfully close. If I would go back and tweak the numbers just a little bit and add a little more income to a couple of the families or one of the families in town B, maybe just the one or maybe two, to change these ranks just a little bit, we might make that significant. So that p-value of 0.05, if I scroll back, is way different than the p-value of 0.40. That's definitely not significant based on the averages. However, based on the rank sums, we almost show that town B is actually wealthier than town A, despite the fact that town A had a mean income of $158,000 versus town B's mean income of $43,660. So what's going on? How does this work? That might be something that you're interested in knowing. So for me, the way I tend to want to work is I would take town A and town B's data. I would sort it. You could sort it in like Excel or whatever. You don't need to sort it because Stata, by doing that command, does all this for you. And my first instinct on sorting it and ranking it would be, after I sort it, you see that the poorest 5 households are in town A. Then we've got town B, and then we rank it 1, 2, 3, and then we adjust for ties, so we call that 3 again. 5, 6, 6, these are tied. We skip 7 and go to 8 because of the tie. So that's how I would intuitively want to rank them. But mathematically, that's not the best way. If I were to do it my way, I would actually then go through and pick out, okay, here are the A ranks and sum them up. Here are the B ranks and sum them up. And we'd have 168 total ranked data points and 62 and 106. That's the way I would want to do it, personally. Now, Stata and some other stat programs, they actually, when you do it the way the software does it, it does it a little differently. Same thing, we sort the data from lowest to highest, and we say, okay, this one's from town A, it's ranked 1, this is from town A, it's ranked 2, and then we have these ties. So instead of giving them 3 or 4, we give them halfway between 3 and 4. We give them 3.5 and 3.5 and then jump up to 5. And then 32,000, 32,000 for town B. Those were tied, so we give 6.5 and 6.5 and jump to 8. We see 38,000. There was one in community A that was that. There was one in community B that was that. So they're tied. They share their ranks. And you do that all the way through. And then you can add up all the ranks that you could expect, which would be 171 possible points based on the ranks. Rank A, or the sum of the A ranks, was 63. The sum of the B ranks was 107.5. Now, if this was a perfect even match, we've got 9 data points from A and 9 from B, and they generate 171 ranked points, then half of those should be for Group A, half should be for Group B. So we would expect 85.5 from Group A. Since we have 9 of them, we'd expect 85.5 for the other one. All right, so moving forward, we see 171 and 85.5 is the halfway point. What did the software predict? The software said we should have a rank sum of 171. We see the software said we have a 63.5. We see the software say for B we should have 107.5. We can go back and look, and guess what? That's what those add up to. And then we see what it expected, which was 85.5 and 85.5. Since this was 171 and we had 9 of each, it should be half goes to each. And then it makes a comparison using 9 observations from A and B and 107.5 or 63.5 using the Mann-Whitney U distribution, and it came up with a p-value of 0.05. So that's kind of how it works. So when you do these rankings, it kind of takes away the leverage of your wealthiest, your millionaire. Your 1.2 millionaire can't skew the data. This person is the richest, so they do count as 18. They count the most, but they don't count like an exorbitant amount more. So they only count as 18. It's just a little bit more than the one that's 60,000, which counted at 17. So this is how we handle non-parametric distributions. A lot of them will focus on the rank and the sum. So that concludes the video on the Mann-Whitney test, and we'll look at some examples of equivalent tests to the paired t-test. So we'll use a paired rank sum test here shortly. So thank you, and enjoy.